So now we're going to be going over how to find the centroid of a region bounded by two functions. So the first thing you want to do when you have a region bounded by two functions is to graph both regions so that you can know where your limits of integration are and what the region looks like. So for us, we have the inverted parabola with vertex at 0, 1, and then we have the linear function x minus 1. So I definitely know that this here is one of the roots of my parabola, which is 1, positive 1. The other root is at negative 1, but that's not the point of intersection for us. The point of intersection is going to be a bit further out here. So to determine that, in order to get my limits of integration for my region, I set f of x equal to g of x. So I get 1 minus x squared equals x minus 1, which leaves me with the equation 0 equals x squared plus x minus 2, factoring. I see that I have a new root, x equals negative 2, and my original root as I saw in the graph. So now I know that this x value over here is negative 2. Next, what I'm going to do is I'm going to find the mass of the region. So my mass just equals the integral from negative 2 to 1 of rho. Again, rho is just a constant, some number. And I just take f of x minus g of x, the higher function minus the lower function. And so what I'll get is negative 2 to 1, rho, f of x being 1 minus x squared, g of x being x minus 1 with respect to x. So if I simplify my integrand, I will get negative x squared plus x plus 2. Sorry, minus x plus 2 dx. So a straightforward integration follows. Negative 1/3 x cubed minus 1/2 x squared plus 2x evaluated from negative 2 to 1. Just some straightforward arithmetic. We'll end up with 9 rho over 2. So this is our mass, our total mass. The next thing we need to do is find our moments of center about x and about y. So just creating a bit more space for myself. So, oopsies. So if I compute m sub x, I'm going to get the integral from negative 2 to 1 of rho, a constant density function. But now I need to take f of x squared minus g of x squared over 2 dx. So I'm just kind of tweaking our formula a little bit to adjust to the fact that our region is not just bounded by the x-axis anymore. It's bounded by a lower curve given by g of x. So if I square and expand, I get 1 minus 2x squared plus x to the 4th. And I get x squared minus 2x plus 1. Further simplifying the integrand, And now I'm ready to integrate. So I'm going to have rho over 2, 1/5 x to the 5th minus x cubed plus x squared. And this is evaluated from -2 to 1. And this is another really straightforward arithmetic evaluation of this integral. And the result you should get is -27 rho over 10. The next step is to compute m sub y, which is going to be the integral from -2 to 1 of rho times x times f of x minus g of x with respect to x. So I get -2 to 1 rho of x, f of x being 1 minus x squared, g of x being x minus 1, will give us a simplified integrand of -2 to 1 rho -1/4 x to the 4th minus 1/3 x cubed plus x squared. And there is a typo in the textbook. The answer is correct, but they kind of, I think there's a typo with one of the exponents, so just be aware of that. So if I go ahead, this is not an integral, is it? So if I go ahead and evaluate this, then what I'm going to get for m sub y is -9 rho over 4. And so now I'm ready to compute my centroid. So the x value of my centroid, x bar, is my over m, which is -9 rho over 4 divided by my mass, which was 9 rho over 2. And if I simplify that, I should get -1/2. And then for y bar, I get my moment about x over my total mass, which was -27 rho over 10, divided by the mass, which is still 9 rho over 2. And that simplifies to -3/5. So in that way, I was able to compute my total mass, my moments about x, my moments about y, and my centroid x bar, comma, y bar. The next thing that we're going to talk about is the theorem of Pappus, which is, I guess, how you say it. Thank you, Google. So the theorem of Pappus says that if you have a region, right, so let's say we're here and we just have some sort of region, and we want to rotate this about a certain point. So let's say this is x equals a. If I want to rotate this around a certain point and create my volume here, then in order to compute the volume, I only need to multiply the area of the region by the distance traveled by the centroid. So the volume equals the area of R. So this area is R times the distance traveled by our centroid x bar, comma, y bar, which is really convenient. You can definitely check out the proof. It works out super nicely. There's a simplification where it kind of morphs into the shell method. If you're feeling, I don't know, tenacious, definitely check it out. It's pretty short. Otherwise, we can just kind of take it on the chin and proceed with the theorem. So using the theorem of Pappus, let R be a circle of radius 2, centered at 4, 0, and then use this theorem to find the volume of the torus generated by revolving r around the y-axis. So what we have here is a circle of radius 2 centered at 4, 0. So if I'm at 4, 0, then I have my circle here, or what should be a circle, right? So this is my region R. And because we're always assuming that our density function is constant across the whole area, the centroid is independent of the density. So it's just the actual physical center of this circle. Well, the center of the circle is just 4, 0. So x bar comma y bar, the centroid, is equal to 4, 0. So now what we want to do, in the spirit of the theorem, is take the centroid and just revolve it around the y-axis. So how far does this centroid travel? Well, one, it travels in a circle, which is great because I know the circumference of a circle is the diameter times pi. And it's also really easy for me to compute the area of the region. So the area of R is just the area of a circle with radius 2. So it's pi times 2 squared, which is 4 pi. And then the distance traveled is the circumference of our kind of pink dotted path, right? So the circumference is a circle with radius 4. So the circumference is 2 pi times 4, which is just 8 pi. Then by our theorem, we know that the volume equals the distance times the area. And our distance was 8 pi. Our area was 4 pi. So our volume is 32. I should write the 2. 32 pi squared. And I'm sure you're wishing you had this earlier when I made you compute the volume of a torus. So anyway, good luck. If you have questions, definitely let me know as always. And thank you for posting to the forum.